Unit 1, Digital Content. Normally I would cover this chapter in more than one lecture session, but since this is an online course that's heavily compressed time-wise, I will be covering it all in a single video. If you're unable to watch the entire video, pay attention to where you are in it so you can resume at that same point. In this unit, we're going to look at digital basics, digital sounds, bitmap graphics, vector graphics, and digital video. In the first section is digital basics. Here we are going to look at 5 different topics: data, representation basics, representing numbers, representing text, bits and bytes, and compression. You should all be familiar with data. If you've ever used a computer, you've probably created data. If you've used a computer, you've made use of data. Data is anything that can be stored inside the computer. That would mean text files, audio files, video files. If you can put it on a computer and store it, it's data. You might be used to making use of your phone or your digital camera to take photographs. Once they're stored on the computer, they too become data. When you store things on your computer, the computer has to convert it into a form in which it can represent the data, and so they can be later retrieved, processed, and so on. Devices such as your phone and computer store all their data in digital format, and it's all handled by the internal circuitry of the device. Digitization is a term you may have heard, but it refers to the conversion process of taking anything that is really in an analog form and converting it into a digital form so your computer can process it. An example of analog is something you can visually touch, like a car or a pet, or maybe it's not necessarily things you can touch, but maybe it's something you hear, like somebody's voice or music. All those are things that you can perceive in an analog form. In order for the computer to understand it, they have to convert that into a form and represent it by numbers, and that's what's referred to as being digital. Now, for a lot of you in this class, the digital revolution probably began before you were born. You know, today's the digital environment affects all parts of our lives. You know, how many people do you know that don't have a phone or other types of electronic device they use on a regular basis? So the digital revolution has evolved through 4 phases, beginning with big, expensive, standalone computers, and progressing to today's digital world in which small, inexpensive digital devices are everywhere. So I guess some of you might argue that some of these phones aren't all that inexpensive, but when you compare them to the price of a computer 30 or 40 years ago, and when you consider what they can do, they're pretty much a bargain. Now, in order for your computer to represent information, it has to convert it into numbers. In the computers, they use zeros and ones to represent data. And these are referred to as binary digits. When you look at a single binary digit, it's referred to as a bit. A bit, or 0 or 1, is used in the digital representation of data. The 0 indicates an off state, and a 1 indicates an on state. If you've ever looked at your electrical appliances you have around the house, you might notice that the power switch on those oftentimes have a circle and a line on them. Those are representative of the digital bits 0 and 1, which is the on and off state. It doesn't matter whether that device is a computer-related device or just an old analog type device that doesn't use computer circuitry or not, they still use the 1-0 representation on those switches. A digital file, usually referred to as a simple file, is a named collection of data that exists on a storage medium such as a hard drive, compact disc, DVD, or flash drive. Some of you may not have much experience using the CDs and DVDs, as they are now kind of fading away. I think the only thing in that generation that still exists are the Blu-ray discs. And with the prevalence of so much online digital content, you might ask yourself how long it'll be before those go away. So there's many ways of representing data. I've already talked about the 0 and 1s. The computers use a code. The one that's most commonly used is referred to as the CISC code, which stands for American Standard Code for International Interchange. And this is an agreed upon set of numbers that we can assign to other values. So they might assign a number to the letter A and another number for the letter B and so on. Inside your computer, it doesn't necessarily see ones and zeros. It really sees, do I have power or do I not have power? And across the board, you'll have a variety of voltages that are used to carry information. So a 1 would typically be a lack of voltage. A 0 would be a lack of voltage, and a 1 would be the presence of voltage. On a CD, DVD, Blu-ray, or any other type of optical media that may happen to come along, the data is stored by burning a pit into the aluminum surface. And if you ever look at one of these discs, you'll see one side that has the label and the other side has plastic. The data is actually written on the other side of the label, and the laser inside the computer would shine through the plastic to identify the pits so that they could bring back a signal. So the presence of a pit would be one state, and a lack of a pit would be another state. So that gives you the ability to represent the difference between the zeros and the ones. On hard drives, they do a little bit different, and these are mechanical hard drives, not solid state hard drives. Mechanical hard drives have metal platters, sometimes they're glass platters, that have a coating of ferrous oxide on them. Inside the drive there are read-write heads that will move back and forth, and they're kind of like the heads you might have on the old style tape players, and they can read the presence of a positive or negative charge. I think you'll probably find before too much longer the mechanical hard drives will phase out in favor of solid state hard drives, which are drives made out of electrical components and have no moving parts. So numeric data consists of numbers that can be used in arithmetic operations. A digital device represents numeric data using the binary number system, also called base 2. And you're probably familiar with other numbering systems. As we've grown up in this world, we've counted from 0 through 10. And if you look at the number of digits you have on your hands, you'll notice you have 10 digits. The numbering system that we're familiar with there is called base 10. The computers also use different numeric bases because the computers can't easily represent things in a base 10 format, but they can really easily do it in a base 2, base 8, or base 16 format. And we'll talk about those more later. So as we talked about before, the binary numbering system only has 2 digits, 0 and 1. So it's really hard to represent data when you only have a single bit. Numbers like 2s exist in the system, so the number 2 in a base 2 numbering system like we've talked about, instead of being the number 2 digit, it would use 1 0 to represent that number. And the way that would work is if you had just a 0, the value is 0. If you have a 1, then the value is 1. But when you have a number that's bigger than 1, you have to go to the next place over, and what's in the 1's place now goes into the 2's place. So the 1 0 works out to having the decimal equivalent value of 2. So here's a chart that shows base 10 versus base 2. And you're familiar with base 10 because that's what we tend to count in, or when we use to do most of our mathematics. But you're really not limited to one base. You could create your own base. If you'd rather use base 3 or base 11, you can do it. You just have to have that many unique digits for that numbers. So in the computers, you see in the right-hand side, we have the base 2 numbers, and you'll see they progress 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and so on, to where we look at the equivalent on the left side, we'll see that we have the decimal equivalent to that. Now, if you're having to use a computer and entering thing in base 2 all the time, you'd probably get really bored. Ones and zeros start getting hard to read after a while. Representing text. So in order for your computer to represent text, like the letter A or the letter B, we have to define some value to give to that, so when it's displayed on your console or screen, it looks like that letter. If I assigned A the value of 63 and 63 popped up on the screen, it's not going to do me any good. So as a general rule with letters and symbols, you can't really do any math with them. With numbers, on the other hand, you can. And it's not exactly true with computers that you can't do math with them, but it'll be math that probably doesn't mean much. So character data could include things like your name, address, hair color, and so on. When you have things of this type, it's typically referred to as text instead of a number. Sometimes referred to as a string. So in order for us to store these things into the computer, we need to agree upon a mechanism to where when I say 63 is an A, you can look at it and agree that 63 is an A. So there are a couple major standards. American Standard Code for Information Interchange is what we typically use mostly on the PCs, although there are times you'll find we also make use of Unicode. The ASCII character set that we use is actually extended ASCII, which represents 256 different values. Unicode is a much larger set, and you can actually store multiple languages worth of character sets in it. So in this case here, it says the ASCII code for the uppercase A is 1000001. And when you look at it, the first one is the ones place and the twos place, the fours place, the eights place, the 16th place, the 32 place, and then the one on the edge is in the 64 place. So when you have 64 and 1, you'll know that the ASCII code for the uppercase letter A is 65. The lowercase letter in the ASCII character set has a different number, so they are not equal. Extended ASCII, which as I mentioned is what we tend to use on our computers nowadays, is a superset of ASCII. The original ASCII only represented 128 characters, and they did that within 7 bits of data. Extended ASCII uses a full 8 bits of data to store a number. Unicode was the other common standard, can provide around 65,000 characters, and it uses 16 bits of data. And with 16 bits, you can actually go to 65,535. I don't know if all of those are actually represented in the Unicode character set. But with that large of a collection of information, you can produce an awful lot of alphabets in there, so you could have for virtually every language that's out there, and probably room for additional symbols. So the Unicode is really useful when it comes to working with multiple languages. Here's an example of what the ASCII codes are, and of course they are really kind and they give us 2 of them in the binary values. But if you look at letter A, which is in the second column about 5 up from the bottom, you'll see that it's 0, 1. There are 5 zeros, another 1, and we know that value is 65. B would be the value of 66. But when we look over onto the fourth column, about the middle, you'll see the lowercase a, and you'll see that it's a different number altogether yet. So it would be a 64 in the position with the first one, 32, and a 1. So if you add those up, you'd get the value for the lowercase a, and you can tell real easily that that's not the same as the uppercase a. There's also a lot of characters that are in this set that are considered non-printable characters that they aren't showing you on this chart. So non-printable characters that would typically be in the character set might be things like printer controls for a line feed, to where I need to go to the next line on the printer. And if any of you guys ever remember a typewriter used to have a roll which they called the platen, and when you pressed a key on it, a little arm would come up and stamp a letter onto the piece of paper that you had on that roller. So when you got to the end of the line, you'd first have to do a carriage return, which brought it up to the first line, and then do a line feed, which takes it back, well, the carriage return takes it back to the beginning of the line, and the line feed moves the roll to the next line. I slightly misspoke there. So ASCII codes are used for numerals, such as social security numbers and phone numbers. So something you can easily represent, that works great. Plain and formatted text is sometimes called ASCII text and is stored in what the book is calling a so-called text file. These files would typically have a 3-character extension of TXT, and if you found one of those on your computers, assuming you're using Windows, and you double-clicked on that file with the TXT extension, it'd probably open a program like Notepad that would allow you to view them. On Apple devices, these files would be labeled as plain text, and in Windows they are labeled as text documents. So on the back here we have a file that it contains data that's stored in ASCII format, and if you look at the raw value in binary, it's pretty darn ugly. When you look at Notepad, which is the box closer to the front, we can see what that information represents once it was actually converted into the relevant characters. That way is definitely readable. I would certainly hate to write that by doing ones and zeros. Microsoft Word produces documents formatted so that Word can make use of them, and it uses a DOCX extension. iWorks on the Apple products or Mac OS. So iWorks Pages produce documents in Pages format. Adobe Acrobat produces documents in PDF format. And the PDF is not licensed solely to Adobe. It's an open standard that allows anybody to create files of this type, and it stands for Portable Document Format. HTML is short for the hypertext markup language, is used for web pages. And it's not the only language that's used for web pages, but it's kind of the base that most people would want to learn if they want to do any amount of web stuff. So here's an example of a DOCX file that's been opened up into a program like Notepad. And you'll see in there that it has a lot of ugly codes. And if you've ever studied HTML for doing web pages, you see that it does have some similar characteristics in that you can see the greater than symbol, less than symbols encapsulating groups of data. And you'll see a similar type of thing when you start looking at markup languages like hypertext or XML. So bits and bytes. And the book does leave a few things out. And they're part of the terminology that you need to learn to kind of understand how computers work. In the computer world, bits and bytes are typically used as a way to delineate what is the capacity of something or the speed in which information can be transferred. So nowadays when we look at things like hard drives inside computers, you're probably looking at how many terabytes does it store. And a terabyte is a big number. So a megabyte would be like a million. A gigabyte would be a billion. And a terabyte would be like a trillion. And a byte, which I really haven't talked about a whole lot, a byte is a collection of 8 bits. And they'll use a byte to represent a single character or value that you'd store into a file. Now the computer's totally fine with bits, but we work better with bytes. Now the one term that's not on here that I really would like them to add to their book, because, you know, the computer peoples of old, just like us, they had a sense of humor. So the smallest part they called a bit. The bigger part that we had used to represent the information is called a byte. But they also have a name for what you'd call a group of 4 bits, and that's a nibble. So when you record to different digital devices, and on this slide here I noticed they're putting out a bunch of numbers for a lot of old devices, like a 1.4 megabyte. That was the capacity of an ancient 3.5-inch floppy disk that very few people have probably used in the last 20 years. Now when you look at 2 terabytes, that might be a capacity you'd look at for a hard drive. And I'd certainly want at least a terabyte of storage space on my hard drive. The first computer that I ever built was back in early 1990. It might have been late 1989, and I had an 80 megabyte hard drive that I put in it. And in that day, that was considered a high capacity device because the typical computer at that point only stored 20 to 40 megabytes of data. They'll also use terms like kilobits, which means thousands of bits. Not to be confused with kilobytes, which is thousands of bytes. If you remember a bit, it's just a 1 and a 0, and a byte is a collection of 8 bits. So if you talk 1 kilobits versus 1 kilobyte, the kilobyte is 8 times larger than 1 kilobit. And you'll see that people, when they advertise products, sometimes they represent them in bits, sometimes they represent them in bytes. Now, a kilobyte of data in a computer, you might think it's just 1,000 pieces of information, but it's not, because everything the computers do are in base 2. And 1,000 isn't something you'd get to by counting on the powers of 2. So you would typically go 2, 4, 8, 16, 32, 64, 128, 256, 512, and 1,024. So on a computer, a kilo is really 1,024. So some of the terms you'll see frequently are kilo, mega, giga, tera. The next one on the list that you don't see would be peta. And you are now seeing more and more of that showing up into the common terminology, because the space that you use to store on computers is getting cheaper and cheaper, and they need a way to represent the data. The last place that I worked, we had set up some servers, and servers are basically just big computers that store data in the petabyte category versus the terabyte that we might do at home. And keep in mind that a kilo is 1,000th of a megabyte is 1,000th of a giga is 1,000th of a tera, and a tera is 1,000th of a peta. So the big numbers. And I guess the one that I didn't get to are ectobytes. So if you see here how they're representing them, a kilobyte is 2 to the 10th power, which is equal to 1,024. So they got a kilobits versus kilobytes. And remember, bytes have 8 bits per byte, so that's really talking about something that's really 8 larger. So if you talked about 1 kilobyte, you would really be talking 8 times 1,024 bits. So a megabyte, instead of being a million, it's 1,048,576. And you notice we go from 2 to the 10th power for kilos, 2 to the 20th power to mega, 2 to the 30th for giga, 2 to the 40th for tera, 2 to the 50th for peta, and 2 to the 60 for exabyte. So if you don't know how powers work, if you saw 2 with the number above it to the second power, it basically means you have 2 times 2. When you see 2 to the 10th power, it's 2 times itself 10 times. 2 to the 20th would be 2 times itself 20 times. So it's just a simpler way of writing a big number. On this slide here, it's various examples of how they could use it. If you were using a computer back in 1990 to 93 and you were accessing online services, because at that point the internet really didn't exist in a way that it was meaningful for most people, you were typically calling up a service like CompuServe or America Online or a local bulletin board. And the 56 kilobits per second was the data transfer rate in which you can connect to that side. And to give you an idea of speed, when you go to the internet nowadays and you pull up a website that has a photo on it, one photo back in the early 90s might take you 30 minutes to an hour to download. For now, we're downloading them at speeds that are typically in excess of a megabit per second, to where it just takes a few seconds at most for it to show up. And sometimes it seems like it's downloaded almost instantaneously. So kilobyte might be the example of the size of a document. When you're looking at faster internet speeds, the next one's, you could have a connection at this speed here, which is 25 megabits per second, which you'll probably find that you can do most things pretty well with. You might have troubles with maybe some of your higher performing games, or maybe if you're doing a lot of uploading and downloading to the internet, you might find it's pretty useless. The service I'm using at my house nowadays runs at 600 megabits per second. And I tell you, after a while, it's really hard to tell the difference. But prior to that, we had 100. We upgraded to 600. All that it really bought us is that it gave us the capability for more of us to get on and do things at the same time. Because my wife, she's a school teacher. My daughter's in college. And we're all using the internet at the same time. So the bigger those numbers are in terms of megabits for your internet connections, that's awesome. And the first time we used this textbook was 4 years ago. And at that point, 100 gigabit for an internet connection speed was probably unlikely. It might have been a speed you could have had on a network, but when you start looking at it now, those numbers are getting much smaller. The next picture that we're showing, well, actually, I guess we talked about the middle one on the bottom, but the one to the left of that has an example of a picture you may have taken from your cell phone. So a typical picture size that we have here, it says, oh, that picture might be 3.2 megabits. And a lot of that really depends on the resolution of the camera that you have on your phone. If you have a 20 megapixel camera on your phone, that size is going to be larger. If you have a 3 megapixel camera on your phone, you might find that the file size might be maybe a half a megabyte, maybe a little bit more. On the last one on the right, the bottom one that looks like the circles, the couple stacked on each other, that's representing hard drive platters, and a typical format might be 16 gigabyte. Now, and I'll make a side note at this point, if you go out and buy a mechanical hard drive or even a solid state drive, sometimes they will mislead you on what the actual capacity is, because as I told you on one of the prior slides, a kilo is 1,024. And some people, when you look like a kilometer in terms of miles, that's 100. So I guess it's not miles, meters. It'd be 100 meters. When they round 1,000, a giga to 1,000, it's misleading, because it looks like you got a bigger number than you really do. So if you went out and bought a 4 terabyte hard drive and installed it in your computer and you look at the capacity, it's really not the 4 terabytes. It's 3 point something terabytes. And that's because of the way they represent the numbers. They've later started giving it a slightly different name so it would remove that confusion. But just be aware, when you're looking at the contents, is the the kilobyte they're talking about 1024, or is it 1000? Now, one of the problems with all the data we store on computers, because computers can store a tremendous amount of stuff. If you put everything out there in a raw format, it takes a lot of space. Compression is a method that you could take to reduce the amount of space that it takes to store that data. There's a variety of ways they can do that. But the whole idea is if you have a file that's 1 megabyte, through a compression process, you might be able to make it only take up a half a megabyte of space. Some types of files will compress better than others. A text document will have a very high compression ratio to where you could take a big file and make it extremely small. But a digital photo, you might find, doesn't compress anywhere near the same unless you throw some of the data out. And we'll talk about different compression techniques later. But the whole idea with compression is to make it smaller. One of the common formats you would see that would store compressed data is a zip file. And it's just a particular format. It's a common one, and it's not the only one. The two that I tend to use mostly would be zip format, RAR format, and GZ format. There are, seems like, hundreds of different compression algorithms that are used to compress these files. So a compressed file will typically contain one or more files. So as I mentioned before, there are different types. And there's two general categories, and depends on what you're doing, one might be more appropriate than the other. If I have data files on my computer and I compress them, I don't want to lose any of that information. So I want to make sure I use a compression that they refer to as lossless, which maintains the integrity of all the data. It just tries to go through an algorithm to determine what is the best way to save space. A lossy algorithm, on the other hand, you'll find commonly used things in image or video files. Your JPEG and MP4 type formats use a lossy compression. And when the person chooses to compress them, they'll tell it, what degree of loss am I willing to accept? You might say, well, 70% of the quality is good enough, and when it decompresses it, it'll fill in the data that it threw out by going through part of that algorithm to figure out what's the best way to fill in the missing pieces. So if you use a lossy compression, you'll lose some of the quality of the information you stored. So it won't be exactly like the original, but if you do a small amount of it, people may not be able to tell the difference. An example, if you're using a 20 megapixel camera or a 50 megapixel camera, and you want to put it on a computer screen, there's way more data stored in that image file than your computer screen can possibly display. So you might give it a 70% compression ratio, display it on the screen, and it's still huge, and you can't tell that you've lost any of that data until you start zooming into the picture to find out, I want to see some of the more finer details. So they're both good in their own ways. When you go to the internet, most of the images that come up on your screen are using a lossy compression. The videos that you see on YouTube typically use a lossy compression. So in order to compress files, you need to have some sort of utility. A couple of the real common ones you'd use in Windows would be something like WinZip or WinRAR, which would allow you to compress. Some of your operating systems will have built-in compression tools with them. They're usually fairly inexpensive, some are free. But compression is a good thing. Now, one thing that Microsoft started doing with Word, and it's been a number of years since they made the change, I think it was around 2007, to where they started compressing their document files. So if you notice, Word documents have an extension of DOCX. Prior to that, the extension was DOC, and the X really tells me that's when they started introducing the compression. And Word knows how to uncompress and decompress those files for you, and the advantage to you gang is it's going to take up less space on your storage. It's also going to take less space when you transmit the file through email or other means. So the process of extracting a file oftentimes is referred to as an unzipping. It's also referred to as extracting. So in the example we show here in the illustration, they've right-clicked on the X Games book materials, and in the shortcut menu that comes up, there's an option to extract all. And what that'll do is extract all that information into the folder that you're currently in. And you can see by looking at it, it has a ZIP file extension. So the type of extension a compressed archive would have in that is usually an indicator of which type of compression methodology was used to create the zip file archive. One of the other advantages you can have with the zip file archives or the other types is you can oftentimes split them into multiple pieces. If you've tried to send a large file over email, you will probably find that most of the email providers aren't capable of sending such a large file. So breaking it into multiple pieces and sending it in multiple messages give the people on the receiving side a way to rebuild it once they've received all the parts. If you've ever used Usenet, which is a part of the internet that's been out there for a very long time, but it doesn't have a fancy graphical user interface like the web does, this is how they generally store larger files, is by splitting them into multi-part archives. Digital sound. The sound you're hearing in this presentation is digital. Yet obviously, as I was speaking, it was analog, and as my computer received it, it converted that information from an analog form into a digital form so it could be stored on the computer. In this section, we'll be looking at digital audio basics, digital audio file formats, MIDI, and digital speech. So digital audio is music, speech, and other sounds represented in a binary format for use in digital devices. And you're using your phone, you're watching videos, you're listening to music. All that stuff is stored in digital format. The photos you take are stored in digital format. Most of your digital devices nowadays have built-in microphones. And that's not always the case. You go back 20 or 30 years ago, a lot of devices didn't have that. But you look at phones and tablets that people are using, they all have the capability of recording sound easily. The way they record the sound is the device would sample the analog signal coming in and convert it into numbers. Once it has it stored in numbers, it can play it back. Now, when you do a digital to analog conversion, some of the fidelity of that sound may be lost. And that really depends on how they do the sampling and how frequently they do the sampling and how big the sampling range is they can use to store it. In the earlier days of digital music, a lot of people complained that the high and low notes were kind of cut off because the sampling range was too narrow. As time has got by, that has improved, but it was certainly a limitation at the time. The first digital music that I recall using was probably in the early to mid 90s. Prior to that, we had things like record players and tape players that we listened to our music on. You might have had digital stuff in the 80s, but not many people had it because it tended to be rather pricey. So a digital to analog converter transforms the digital bits into analog sound waves, and you need that so you can hear it. Because if the computer just played a bunch of numbers, are you going to know what they mean? But if they convert it back to a sound that number represents, then it's going to sound a lot like the original. It probably won't be the best. You'll probably have heard of some people talk about how they like the sound of a record as being better than digital audio that's recorded some other way. I have a hard time telling the difference, but I know some people that are really pretty good at it. So in this slide is what it's trying to illustrate. On the left-hand side of the screen towards the top, you have an analog sound wave. This might be a sound from a musical instrument or a spoken word coming from a person. But in order for your computer to convert it, it samples that at an interval And for each of those samplings, it stores it as a number. So if you look at the chart on the right, you can see that if you start connecting those little lines, it's kind of a jagged looking diagram, right? So if you have a very low sampling rate, the audio is going to sound terrible. If you have a high sampling rate, it's going to sound a lot better. And for the sampling rate they'll typically refer to is how many hertz was it recorded at. So if you had something recorded at 115,000 hertz, it's going to sound a whole lot better than something that's converted at maybe 43,000 hertz. A hertz is just a fancy way of saying cycles per second. And what this slide's trying to illustrate, it shows an audio file that's sampled at different sampling rates. On the very top, where they call it good, and most of us nowadays would probably call that poor, you can see what that audio file might look like if they graphed the sound that they recorded. So that's sampled at 11,000 hertz, 11 kilohertz would be 11,000 cycles per second. The better, which is the one right below it, is 22 kilohertz, which is 22,000 cycles per second. And the bottom one, which is the best in this example, is 44.1 kilohertz, which is 44,100 cycles per second, or samples per second. And right below that, they represent, for those small file size, the relative difference in file. On the top one, the file size is 66 kilobytes, 124 kilobytes for the better, and 235 kilobytes for the best. And that's something you want to keep in mind if you're recording something. The higher the sampling rate is, the higher the amount of storage is going to be required to store that information. Now you'll find there's a whole lot of different file formats for different types of audio. In order for your computer to understand what's in them, they must contain a program that's referred to as a codec, which basically means it knows how to encode and decode the signal to where it's understandable to you. If you've ever grabbed an audio or video file and tried to play it and your computer didn't know what it was likely recorded using a different codec. So on this slide, they have a variety of different formats. There's hundreds more that aren't on this list. And even within there, like the top, they talk about AAC and MP4. Even within MP4, there can be multiple codecs being used to record different types of MP4s, where one codec may play one MP4, but it may not play another. So what I usually do to have a reasonably rich set of codecs on my computer is I install a video player called VLC. I don't know if there's any better ones out there, but it does come with a pretty rich library, and I know it does not contain all the codecs. I limit myself to what it can play, and the reason why I do that is a really good way to get your computer infected with unwanted software like a virus is start installing things from less than reputable sources. And it's not easy to tell which sources are reputable. So that's why I figured VLC is a pretty safe place to be. If it doesn't play within the VLC player, which is a pretty common tool and works across all platforms that I know of. At home I use Linux, I use Windows, and I use Android, and it works in all of those environments. In order to play audio software, you have to have things. So the first thing they have in here is audio software, which is a general purpose program like iTunes, which allows for recording and playing of software. An audio player just allows you to play the audio file and not necessarily the ability to record it. And audio plugins, those are kind of like the codecs, because without the codec you can't play some of the files back. But some of the programs, especially the older day web browsers, required audio plugins in order for you to listen to different types of audio formats. You know, years ago, before we changed to HTML5, YouTube used to use the Flash player to play videos. So in order to play those, you had to install the Flash plugin into your web browser so you could watch those videos. Now, Flash had a lot of problems, and I'm glad it's no longer required for YouTube. But I think you get the idea there. So how do you listen to audio files? Well, you can download them to a device and play them. And if it's something that I purchased, I'm definitely going to download it. Sometimes you can find free things out there you can download, but just because you can find it available for a download doesn't mean you necessarily have the rights to use it, and we'll talk more about that later. A live stream is it's being broadcast, and as they're broadcasting it, you're listening to it across the web. A real common example of a live stream is somebody streaming a video over YouTube, to where you have not only the audio, but you also have the video as well. They could live stream an audio show, like a radio show. An on-demand stream, a good example is Netflix or YouTube, to where there's a variety of videos out there. I can pick them, listen to them anytime I want. Pretty good deal. So you have your options. So the first one, the audio is on your device. It does not require an internet connection to play them. It only requires the connection to download them. Live stream and on demand, you actually have to have a real connection. Some of you may have heard this term before, and that is ripping. And this is referring to using software to extract audio files off of things like a compact disc or a DVD or a Blu-ray. And this is legal to do, providing that you don't have to break any encryption formats on the device. So if you have music CDs and you want to have the music on your computer, so long as you don't have to break any encryption to do it, you can rip the content. But you can only rip it for yourself and for one device. It's one of the early laws on computers allowed you to make a backup copy of any digital software or content that you had. Later, another law came along that says if it's encrypted, you can't decrypt it, short of running it through the normal means. So if you're trying to copy the files off because of the encryption or the digital right management that's done with that product, then it's not legal. And of course, if you rip music, you can't share it because you're only allowed to have the one copy. Now, the exception would be is if the makers of that audio format or video format gave you permission to share it, then that's a different story. Now, some of you may play musical instruments. There's an old interface type which is still in use. It used to have a special plug that you'd use on the computers. Nowadays, most of the computers do this through the USB or universal serial bus port. It allows you to hook up a digital instrument like a keyboard or a guitar to a computer, and it allows it to record the music from the device, or you could even compose the music on that device and play it back on the instrument. So it's pretty nice. It's been around for a long time. Here's an example of a product called Finale in which they are composing MIDI music in the software. And this would be something you might play back through your keyboard or guitar, or even through your computer speakers. The musical instrument is not required to use the MIDI files to listen to them, but if you want to play them back through the device, you do need to have that connection. Digitized speech is when the computer would speak to you based on, at least the way they used to do it. They used to have little sound libraries that they would piece together to rebuild words. So the computer would speak back things, and it might do that based on the contents of a document. Nowadays, the computers are as powerful as they have. You could actually record each individual words, and then the computer could play them back for you. Speech recognition is the reverse of that, and it's probably the harder of the two. And especially when you consider how most people sound a little bit different. Some people have accents. Some people don't enunciate their words as clearly as the others. So in order for speech recognition to work, the software has to be able to represent those different mannerisms or types of speech that people would have. A common application of speech recognition might be using something like Siri or Alexa, to where you talk to the device and it will respond based on what your request was. And if you've ever noticed that sometimes they don't recognize you, it just goes to show that speech recognition still has a ways to go. When I was in college, we played around with this. This is back in the 80s. And in order to get the computer to recognize speech, we'd have to train it for every word we said to the computer. And you might have to train it 8 or 10 times. And then when you say the word, there's a high probability that it would still get it wrong. To where nowadays, it doesn't take a lot of training. The devices are pretty good at doing it, but they're not perfect. I think I've covered most of what's on this slide, so we'll go on to the next one. So here's what I was talking about. They're talking about different sources. Here in this case, it's Siri, and it's kind of explaining how Siri works. So I will skip this slide as well. Bitmap graphics. If you have a graphic or a picture stored on your computer, it's in a bitmap format. And we'll talk about what bitmap format is. And in this section, we're going to look at bitmap basics, bitmap data representation, bitmap resolution, image compression. And remember, we talked about both lossy and lossless, and we do the same thing with graphics. Depends on what your intended use is. And we'll talk about modifying bitmap images. As digital devices gain the ability to display images, two types of computer graphics are involved. We have bitmap and vector. In a bitmap graphic, every dot is stored as a pixel or a picture element. And in a vector, it contains points and then connections between those points. And it gets a little bit more complicated than that. The bitmap graphics, if you zoom in, eventually they start getting jaggy, and we'll see some examples of that in the later part in the presentations. But in a vector-based graphic, and this is something that's commonly used for storing of fonts on a computer, you can keep making it bigger and bigger and bigger without losing any quality. So within the computer, a bitmap stores every dot that it takes to build the picture, and when you look at your computer monitor, it's really a series of rows and columns, but there's a lot of them. And it takes, if you have a 1080p monitor, it'll typically take 1920 by 1080 pixels. And if you took the two, one is the horizontal and vertical measurement of pixels, you multiply them together, that tells you what the total number of pixels are for that screen. So each of those picture elements is referred to a pixel. Each pixel that is stored will typically have a color stored with it. And there's typically, depends on the formats, most of them will be around 16 million or so colors. And that makes a pretty convincing looking picture. So here's an example where there's a picture of Stonehenge in the background, and they zoomed in to the top of that one rock. And you can see where the circle is. The image you see on the front is an example of what that would have looked like as you zoomed in that far, and you notice the image is no longer clear. What is probably hard to tell is each of those squares are only a single color. It's not a shade of colors. Each square is one color. Your mind kind of makes it look like it's more like it's shaded, but it's really not. Now in this image, it's possible that it is shaded, but when you zoom in on an actual graphic, there is no shading. Each pixel is one color. And even the paint program that comes within Windows, you have the ability to zoom in like this and get down to the pixel level. When you zoom back out, because it's so far away, it looks pretty darn good. You can create the bitmap pack graphics from scratch using programs like Paint. I believe I gave you some software links under announcements for other graphic software you can use, like the GIMP and Paint.net, which are free products. The GIMP is cross-platform, which means you can use it on Windows, Linux, and Mac OS, to where the Paint.net, it really only works in the Windows environment. And they're way more powerful than the software that comes with your operating system. The GIMP is probably close in power to programs like Photoshop. And like Photoshop, it has a fairly high learning curve to really get the handle on how to use it. I know people that use Photoshop that say, oh no, Photoshop's a lot better. And I know people that use GIMP that says GIMP is just as good. So I'm not in a good position to say which is better, but I do like spending less money, and the GIMP is free. So one way you can get something into your computer is to put it on a scanner and scan it in. Pretty easy to do. You could just take a picture of it with your phone, but it may not be quite as good. Or of course, a picture you do take with your phone is one way to get something into your computer in graphic format. In talking about your digital cameras, there are some variances on how this works. In the slide, we're talking about a charge-coupled device, and that really talks about the circuitry inside the camera that is used to capture the image. And it's typically behind a lens, and that is used to capture it. There's at least one other technology, I can't remember off the top of my head what it is. It works like the CCD does, but I do know things like in security cameras, the newer ones are moving away from the charge-coupled devices to this newer technology. So the photos that are captured by your phone will typically be stored in a format like JPEG, GIF, PNG. If you're using a camera, it will probably have, at least a higher end camera, would store it in what they call a RAW format, which is basically all the raw data without any compression to it at all. That in order to share it beyond other people that have the software like Photoshop that has the capability of understanding raw format, you'd probably have to convert it to a more portable format like PNG or JPEG or GIF. So I think I've already mentioned before, the higher the resolution of the photos, the larger the number of pixels. You know, in the camera size, 8 megapixel, for example, can produce an image that's equal to 4K video. Now your computer has a limited set of colors that it can deal with, and the ways we would typically do here is an example where we have, on the bottom we have these 3 different sets of colors. We have red, green, and blue, oftentimes referred to as RGB, which is short for red, green, and blue. And by indicating how much of each of those colors you have, you can produce another color. So in the example on the left, white, we have the maximum amount of red, green, and blue, which is 255, and that will produce a white color, which is the color you see in the center. The way the computer would store that in binary digits over 3 bytes would be 24 ones. Or using the hexadecimal, which I haven't talked about, hexadecimal is base 16, which represents numbers starting at 0 through 9. And when it gets to the 10th position, it uses the letter A, 11 is B, 12 is C, and so on, and F is 15. And the reason they do that because there's a 1-to-1 correlation in hexadecimal or base 16 as there is in binary. 2 hexadecimal digits are equivalent to 1 byte, which is 8 bits in binary. So computers like to do things in base 2. The example we have on the right for the color violet, we see we have 238 value for the blue, 238 for the red, and 130 for the green, which produces the violet color you see on the screen. And this is the same methodology that most of the monitors or display devices we use, whether it's for a phone or a tablet or a computer screen, is they use this type of method to paint the information on the screen. So you get a white by having everything on. You get black by having everything off. So a black would be 0 of each of those colors. So I've already talked a little bit about the different values. Color values can be specified in base 10, which is the numbering system we're most commonly familiar with, hexadecimal, which is base 16, which I briefly explained on the prior slide, and binary, which is base 2, which is stored in ones and zeros. So with 8 bits, using those 3 different colors, it'll require 24 bits to store the color for 1 pixel. The number of colors available in a graphic is referred to as the color depth. And the color depth with 24-bit is 16 million colors. Or actually it's over that, but it's close to 16 million colors. The dimensions of the grid that forms a bitmap graphic is referred to as the image resolution. One example that I gave you of this earlier is I talked about 1080p, which is 1920 by 1080 pixels. So the higher the resolution of the graphics, the more pixels it contains. The lower the resolution, the less pixels it contains. The higher the resolution of the graphic, it's more likely you're going to have a sharper and clearer image as compared to a low resolution graphic. So if you look back, remember back to the picture of the Stonehenge, when we were zoomed out, it looked pretty high res. When we zoomed in, it looked pretty low res. So the different graphic softwares oftentimes will give you the ability to adjust the image size. And as you adjust it, you can't add quality to what's not there. So if you increase the image size, it's going to have to fill in the blanks with something. If you decrease the image size, it has to throw some of that stuff out. The reasons you would typically resize an image is maybe I want to use an image for like a well, like in Canvas, you want to upload your photo. You might have to scale it down to a lower resolution photo before you can upload it, because there is a maximum file size associated with your profile photos. Of course, the more you do that, the more the quality of the image will deteriorate. Image compression works just like any of the other compressions. Is you have 2 basic types. You have lossy and you have lossless. Run length encoding, or LE, is a type of lossless compression that replaces a series of similarly colored pixels with a binary code that indicates the number of pixels and their color. And that's a real common method they use for compressing, is just looking for things that are in common and just give a reference to them instead of storing each of the individual bytes of data. So in this picture here, it's really hard to tell the difference, but if you look closely, the one on the left is a non-compressed JPEG, and then the one on the right is slightly compressed with a 35% compression ratio. And if you look at the one on the right, you can see that some of the quality isn't quite as sharp as the other one. It's hard to tell, but if I went to like a 50 or 75% compression ratio, the difference oftentimes becomes very obvious. The other thing you'd notice if you ever did zoom into these videos, you'd find that the JPEG on the left has much more depth than the one on the right. So you would lose clarity quicker zooming into the 35% one than you would on the non-compressed version. So this one's talking about photo editing. So Photoshop software is a host of local and online apps which make it easy to modify digital images. And if you buy Photoshop nowadays, you'll find that Adobe, which is the manufacturer of Photoshop, likes to do subscriptions. So you kind of have to subscribe to it, and there's an annual fee. It's not outrageously expensive, but the cost just keeps reoccurring. That's why I prefer, when I can, to use free software. And there's a lot of really good free stuff out there. Photo auditing software can include sophisticated tools based on graphic design algorithms. And whether you're using Photoshop or the GIMP, they have some pretty amazing capabilities within those. Unless you're doing professional editing, you'll probably find either one would meet your needs or exceed your needs quite easily. And this slide here illustrates some of the types of things that the software might do for you, like reduce noise, which if you've looked at some of the old pictures and you start looking at them through a magnifying glass, you'll see little artifacts that really don't belong there. That's noise. And the noise reduction is the capability of the software to kind of blur those out till you don't really see them anymore. You know, image enhancement, an example might be you took a picture of somebody and their eyes are glowing red, and you want to get rid of the red eye. And there are features within a lot of the software to automatically do some of that for you. So a lot of features, it'll vary from product to product, One product is going to give it one name, another product will give it another name. They're all going to have similar types of features. You just have to figure out what they call it in the product that you're going to use. Vector graphics. One example I gave you of vector graphics where TrueType fonts is what you typically use on your computer for looking at letters and numbers. In this section, we're going to look at vector-based graphics, vector tools, and 3D graphics. So in this illustration here, we have a group of shapes. On the first one, we have lines. In order to store those as vector, all you really need to do is record the 2 points and how to get from one to the other. Likewise for the shapes or the fills, instead of giving all the details or all the pixels, it just gives them the details on what does it take to make the shape. So probably in the filled shape, it's probably the 4 corners and then what the fill color is. So you don't have to store all the stuff in individual pixels. So I can take that shape and I can stretch it and shrink it, and it looks just as good no matter how big or how small it is. The gradient filled shape, similar to the other shape where we have the basic coordinates to build the shape and then the pattern that we want to use to fill it. Now the gradient fill might vary a little bit as you stretch it, but the shape will still look good. You can create 3D shapes, which will be using both the X, Y, and Z axis. And then you can have a gradient filled shape. So those are all examples of vectors. So a vector graphic consists of a set of instructions for creating a picture. The vector graphics include starting shapes, such as circles and rectangles. Vector graphics versus bitmap graphics. Well, you cannot do a really good job of resizing bitmap without losing some of the quality. So you're going to find vector graphics resized much better. Vector graphics also take a whole lot less space because I don't have to store every little pixel. I just need to store the information that it takes to recreate the shapes and the shading and the colors. Your vector-based graphics oftentimes are not as realistic as bitmap graphics, but some of them look pretty darn good. Now, to create a realistic vector-based graphic, it's going to take a lot more time than it is going to do to create a realistic bitmap graphic. One of the things you can do in vectors that you can't do in bitmaps is you can create an object like a car and rotate it and see it at all different angles. On a bitmap graphic, it doesn't have that dimension to it. So if you're playing games, you might find they use a lot of vector graphics in it. Editing objects is oftentimes easier than in a bitmap. Because in a bitmap, a lot of times you're dealing at the pixel level to make changes. To where in the vector graph, well, you're just moving points around. So here's some examples of different types of vector-based graphics. On the top right corner, we have the letter B, which is an example of a TrueType font that you would use in your computer. On the bottom has an example of a floor plan that you might use maybe in designing a house. Clip art oftentimes use vector-based graphics, and some of those look like the clip arts that you might use in Windows. Or on the bottom corner we have a chart which looks like something you might have created in a spreadsheet. There's a lot of different tools for doing vector graphics. Adobe Illustrator, LibreOffice Draw. Now LibreOffice Draw is a free product. Open source Inkscape, I don't have any experience with that one. And there's other types of vector drawing apps. Even your computer-aided design software like AutoCAD or Autodesk are vector-based products. So 3D graphics are graphics that have not only height and width, but depth. And I mentioned before that with vector-based graphics, it's much easier to build three-dimensional items. So vectors can form a wireframe, and you may have seen examples of where maybe they built wireframes of objects like cars, and they filled those wireframes on by putting a skin on it, and it made it look to a large part like a real-life object. And it really depends on how good a job they did on rendering the texture for that wireframe on building the surface. So the techniques for adding lights and shadow into a 3D image is called ray tracing, where they'll pick a point that the light would originate from, and then it would emit towards the direction of the objects, and the object points that were closer, like in real life, would be brighter with reflections and stuff. So you'd see an example of how this would look in real life. If you looked at a car sitting in the sun, you could see that different parts have different amount of lightness on it based on their relative location to that light source. So here's an example of an image that they are rendering a skin for. In this case, there's a wireframe of a car, and they're going to put a skin on it so it looks realistic. Now the image quality here is really poor. They can do this extremely well, and the images look just pretty amazing. You might have a hard time differentiating it from a picture of a car if they did a nice job with rendering the skin that goes on the wire frame. One of the things you can do relatively easily with 3D graphics is you can animate them. A 3D graphic would typically be stored in a 3D dimensional matrix, and there's mathematical operations you could perform against a matrix to actually get an object to move and rotate. So it takes a lot of processing powers, and if you've bought one of these higher end video cards, this is something the video cards will take on the workload and do very well with. Now, some of you may have played the newer versions of Doom, but the original version of Doom, I believe, came out in the latter part of the 90s, and they did a pretty good job with their 3D graphics. They used 24-bit colors, which requires 3,560,000 bits for each frame of animation. Now, one of the tricks that a lot of the game makers will do is, instead of rendering everything real time, they might go through a variety of different phases and capture the image for what it looked like at each of those rotations. And then it's faster to display that image than it is sometimes to compute the next viewpoint. Because there's a lot that goes into rotating a three-dimensional image. Digital video. Most of you have probably done some of that with your phone. If you look at all the videos you see of people capturing things in real life on YouTube, oftentimes it's exactly what they did it with. So in this section, we're going to look at digital video basics, video compression, and video file formats. So digital video is not all that much different in the kind of the way they approach it than what they did old day films. In the old days films, they would have a mylar tape with basically images on it that they'd run in front of a projector. And by going through these images quickly, it looked like the items on the screen were moving. And that's exactly how the video works on your phone or your computer. It's a series of images. It's a little bit more complicated than that. If you're playing games, a lot of times they'll talk about frame rates, and that's talk about how many frames are displayed, how frequently they're displayed. And the higher that number is, the more lifelike it looks like. If you go back to the old TV days, they're typically only displaying things at a rate of maybe 30 frames per second. If you're playing a game, you probably want 120 or higher. Some people find it's easier to tell the difference between high frame rates and low frame rates. Some people have a difficult time doing that. So there's different ways you can capture the video. Your cell phone camera is probably the easiest way. If you're using Zoom, you might capture using a webcam. Or you can go out and buy one of these really expensive, like the Red cameras, that create really high quality videos. It's a lot of money too. I think they're like $20,000 or $25,000 to get started. Digital cinematography uses used in the motion picture industry, capture moving images at bit rates rather than on film. They used to capture it on film. I know when they first started changing, that was back in the early 90s, the people that were using film didn't like digital because they said you never could get the same quality with digital as you do with the old analog film. And as you see nowadays, that because of the quality of digital has increased so incredibly much that it's a pretty nice way of doing it. So we do use digital video for a lot of things. The video that you're watching now is stored in a digital video format. Your digital television nowadays typically would be like 720p, 1080p, 4K. Now the 1080p is also referred to as 2K. So here's an example of film to where it's a series of individual pictures, and by moving the frames, it appears that we have real life. So they say on the bottom end is the frame rate for the early 3D games, maybe 6 frames per second. Standard motion pictures had 24 frames per second. Standard frame rate for YouTube videos is 24 frames per second. Frames for The Hobbit and Unexpected Journey, they used new processes at that point, which they filmed at 48 frames per second. Broadcast television, 60 frames per second. And acceptable frame rates for modern video games. If you're a game player, you're probably going to say 30 to 60 frames per second isn't adequate, and I need a better video card to fix that. And at the bottom, say 60 maximum frame rate for YouTube videos. Maybe, I'm not sure what the maximum frame rate is. So that's typically measured in frames per second. So video resolution could be expressed as width times height. So common format for digital camera, at least in this example, would be 2040 by 1536, which is a little bit better than a 2K video. The vertical resolution expressed with a P refers to as a progressive scan. And what a progressive scan does is it paints half the screen, then it paints the other half, to where an interlaced scan paints from top to bottom. No, that's backwards. Progressive, top to bottom, interlaced, paints half, then goes back and paints the other half. So this here illustrates the difference between a P and an I. So the P is generally considered better. And the I is kind of what the old standard was, especially for the old television sets that received a signal across the air, is that they would receive the interlaced message. So it would paint lines 1, 2, and 3, then it go back and paint lines 4 and 5. To where you can see in the top one, it starts from the top and goes down. So one's called progressive, the other's called interlaced. You may or may not be able to tell the difference. Now the aspect ratio describes the shape of the image. Old style television sets used an aspect ratio of 4.3, which is 4 units wide, 3 units high. Most common monitors and laptops will use an aspect ratio of 16:9, which means 16 units wide, 9 units high. There's all sorts of aspect ratios you can use. 16:9 is common. The monitor that I have on this computer actually uses a 32:9 aspect ratio, so it's a really wide screen. So this example is talking about 4:3 videos when displayed on different types of things. So when 4:3 videos are displayed on a widescreen player, they are bordered with black bars. So those black bars can either be on the side or on the top and bottom, depends on how they were recorded. So if you looked at a 16:9 video on a 4:3 screen without stretching it to fit, you would have a letterbox on the top and the bottom. So this is giving an illustration. The letterboxing is the black area that you're not displaying the image. So this gives you an idea of some of the different resolutions you typically find. A 16:9 aspect ratio. The very top one, we have 3840 by 2160. This is the resolution you typically have with a 4K monitor. So 4K or 2160p. The 1920 by 1080, the third down, you have 1080p, which is also like a 2K video. And that just refers to the rough number of bits that it takes to display that information. So you don't see a whole lot of 4:3 devices anymore. Most of them have pretty much migrated into the 16:9 aspect ratios, but they still exist out there. So that first one's a big number. 1.1 billion bits are needed for 1 second of digital video. And that really depends on the quality of the digital video. If you record it in 4K versus 2K, it's going to take about 4 times the amount of space relative to the other one. But the point here is video can take a lot of space. If you're using a double-side, double-density DVD player, 8.5 billion bits was pretty typical. Trillion bits is typical, 8.5 terabytes. The bit rate for a number of bits that are processed, the bit rate is the number of bits that are processed during a specific unit of time, which is usually 1 second. So if you see something with a KBS, no. Yeah, that'd be kilobits per second. K bits would be thousands of bits per second. A higher bit rate generally would indicate probably a better image. So advantages of choosing lower resolutions. If you're at home and everybody's struggling for bandwidth, if you are watching everything on the higher resolution videos, if you scale down that video resolution just a little bit, like if you took it from a 1080p and made it 720p, you'd find that it only takes half as much data to display that film as it did the one at the higher resolution. So that might be one way to help mitigate issues if you're having that. We've talked about compression, in that there's 2 basic types. There's lossless and there's lossy. Most video formats you use are using a lossy compression. MPEG-4 is basically a variant of a JPEG. A JPEG is a type of graphics that use lossy compression. MPEG or MPEG-4, MP4, uses lossy compression as well. And if you only throw out a little bit, most people can't tell the difference. And they do that to reduce the size. So compression removes some of the bits through the following techniques. They got image compression, where we have frames of videos that are compressed using lossy or lossless compression. And they have interframe compression, which is kind of a cool way of doing things, to where you store only the pixels that change from one frame to the next. So if most of the picture isn't changing, you only have to change the parts to move. And that takes a whole lot less space. And by doing interframe compression, you aren't necessarily going to lose as much data, but still reduce the size considerably. So I mentioned a codec before. Codec is short for compressor decompressor, and it's the software that you need to either record or play back video. So it might be something you'd use for stored videos on your computer, for watching videos on a stream like in YouTube. So each codec is unique in that they have their own special way to encode and decode those videos. So one codec will not necessarily decode a video made using a different codec. So some of the common codecs, I've already mentioned MP4, we have MPEG, VPH, DivX, H.264, there's a bunch of them out there. WMV, which is the Windows Media Video, really common. Video files that are stored in container formats that hold compressed video streams and audio streams. So we have MP4, AVI, MOV, MPEG, WebM, ASF, VOB, and there's a whole slew of others. And this is basically representing the same thing here. If you download a video that you can't play, it might just be, it's not the bad video, it might be you just don't have the right codec. Most browsers have support for a certain amount of these video formats. An example would be Internet Explorer, Edge, or Chrome, or Firefox, to where maybe you go to YouTube and you want to play a video. There's built-in capabilities, at least in the way HTML5 works, that allows you to watch those pretty easily. Some of the others you may need additional tools or plugins to make it work. It's pretty easy to convert digital videos from one format to another. It goes through a process referred to as transcoding, which in order to do that you have to have the codecs for what it's made in as well as the codec you want to make it in. So you can use video editing software. One of the tools that I'm using for this class is called Camtasia. It's a really good tool that helps me with not only capturing the videos, but if I need to come back and add annotations or other features, it's real easy to do. It also allows me to cut out sections if I don't like a part of a video, that I could take out a section and add a new section in its place, or just totally remove it from the slide. So here's a product that's called My Movie, or Movie Maker. The name of the file is My Movie, and I believe Movie Maker was a product that came with older versions of Windows. I don't think Windows comes with it anymore. But as I generally feel that most of the free stuff that comes with Windows, most of it is not really good, and I still want something better if I'm going to do any amount of it. But in there, as you can see, you do have the ability to take parts of one video to make it into another. You can also take multiple videos and stitch them together to make one longer video. And you'll see this is something that's commonly done on YouTube when people make compilations. That's exactly what they're doing, is they're taking video segments from different sources to make their own. Not always original, but people do what they do for whatever reasons they do it. I don't know what to tell you. All right, so that's the end of Unit 1. If you didn't make it through the video all at one point, you might want to keep track of where you lost your place, or you can go back and rewatch it as many times as you want. So it's hard to make these short. There's a lot of material that comes with each chapter. I will be producing one video for each unit in the book, and this textbook has 11 units. So thank you very much, everybody.